Thank you, Cody, and thanks for the organizers. It's been a nice workshop, a new experience for me as well to speak in one of these. Right, I'm talking about unbiased estimators in multi-level Monte Carlo, or maybe kind of unbiased versions of multi-level Monte Carlo. And that's quite classical. What I try to do in the middle of the presentation, I try to connect this also why these unbiased estimators may be actually interesting in the Bayesian inference setting and some other settings. So that connects to the thesis talk as well. And then I'll present some of the new schemes which I have, which are slight modifications of the previous ones. And so, yes, I'll just start with a very classical setup. So my talk will be infinitely more simple than thesis because I'm doing one-dimensional inference, at least to begin with. So y is just the real value random variable. We care about the expectation. We can't simulate y, so we can't do direct Monte Carlo. We don't have the density or the unnormalized density, so we can't do many of the other methods like rejection sampling, importance sampling, or MCMC, at least directly. But what we can do is that we can simulate approximations of y, which are as accurate as we want if we increase the L, the fidelity of the approximation, or refine the mesh. In most cases, that's refining the mesh as well. So L stands for the level. Yeah. But the thing is, of course, that the computational cost of realization of one random variable YL becomes more and more expensive when the level is increased. And this is a canonical example which we also saw a few times yesterday, which is just the SDE, or a diffusion process. And basically a canonical example of multi-level Monte Carlo is we want to approximate the expected value of a functional of the terminal state of a diffusion process. And this is sort of exactly falls to the setting. So unless we have a specific form of the drift, the diffusion coefficient, or the function, we can't calculate this expectation analytically. And also it's impossible or very, very difficult and computationally expensive to calculate, to simulate exactly the diffusion process at the final time. And we don't have densities available. But we can simulate very, very easily discrete time approximations of the process. And the usual thing is we take a uniform grid, say with 2 to the L points. I will have this example later on as well. So I will have level L 2 to the L points, time grid with 2 to the L points. So the cost of one realization will be just order 2 to the L, right? The number of time steps. And then there is some error rate, how the bias vanishes when we increase the level. If we would do direct simple Monte Carlo, that would be just choosing a level and simulating n samples. So the thing is roughly just that, as we probably, you all know, because this is a multi-level workshop. So basically, the simple Monte Carlo suffers from 2 approximations in a way. You have an average that approximates an expectation, and that expectation approximates another expectation, which is the one we care about. And therefore, we have 2 error terms. And turns out, even if we sort of choose N and L in an optimal way, so that you have a minimal MSE with a fixed computational budget, you will always have worse error rate or worse MSE than the canonical Monte Carlo rate would be. So I'm talking all the time about the rate at the mean square error vanishes as you increase the cost. So this is, of course, the If you like the computational complexity, that would be O to the epsilon minus 2. Okay, and of course, multi-level can help a lot in these kind of settings. So instead of the simple Monte Carlo, what we can do is that we can look at this telescoping decomposition. So I'm going to use the convention that y naught is going to be just 0 to simplify notations a little bit. Okay. So basically, what's the point of this telescoping decomposition? Trivial telescoping decomposition here is that we can actually approximate each of the terms separately by a Monte Carlo estimator, involving replications of a random variable delta L that sort of can be used to estimate the difference of the expected values of the y's, the approximations at consecutive levels. And roughly speaking, why is this actually useful? Well, you have more freedom to optimize. You can optimize all the n's and also the final level m. But very, very crucially, also the delta L's can be chosen to be really, really small in absolute value, even though the YLs are quite large, by basically coupling the YLs and letting delta to be their difference. And in the SVE setting, it's very, very simple to actually have a good coupling, which is very effective as well, just by simulating the random variables y, using same Brownian path or same random variables, same normal random variables to simulate the discretized versions of the SDE. And if we use the Milstein scheme, we get a rate for the square expectation of the deltas to be quite nice, so it actually decays as 2 to the minus 2L. And in this setting, when you optimize, the multi-level can actually reach the canonical Monte Carlo rate, which is nice. And this is always true when you have the strong rate bigger than 1. And there are schemes that actually satisfy this in a reasonably general setting. So, okay, so what are the unbiased estimators? Maybe they are rather similar to the multi-level Monte Carlo. So you have the same. I'm using the same letters even here. So I have the same thing. I have YLs that approximate Y. I have delta L's that sort of approximate or encode its expected value is the expected value of the level differences, and I'm also having the 0 level being 0. But what's different? So instead of the n's, NLs and the m, the number of samples in each level and the terminal level, I only have a probability mass distribution, or a probability mass function, which is it's a probability distribution on the positive integers. And the scheme is super simple, or the simplest scheme is super simple at least. And the simplest scheme is just that you pick one level of a random variable r, which will be your level at random from that distribution PL. And then you also calculate the corresponding delta corresponding to the level r that you pick. And your estimator is like so. It's just a ratio of that level that you picked and the corresponding probability that the R takes that particular value. And this is called the single term estimator. It's rather simple actually to sort of formally see that this is unbiased by just writing the estimator as this sum. Yeah. Because basically this indicator is only one term, which is exactly that one. So basically this is just a rewriting of the Z1. And then if we can interchange the sum and the expected value, we can do this. And by independence of R and the deltas, you get this separate. And actually this probability here will be exactly as the PL in the denominator, so these will cancel. You will get the telescoping decomposition that actually has the right value in the end. But this is not a proof, so the start step here is not, you have to have conditions to be able to do that actually. But in the paper of Chang-Han Ri and Peter Glynn, they actually did a nice result where they have this condition, which is saying basically that if this quantity, which I call V here, so it is just the squared expectations of the level variables divided by the corresponding probability of picking the level. If this quantity is finite, then you do indeed have an unbiased estimator, but also actually the variance is basically determined by the V variable, or the V quantity V here, so this sum. Right, so on top of that, so in the randomized setting, of course, there is another thing. So this estimator, because it is actually you pick by random the level you are going to simulate. So this will have a random cost. But it turns out that the right thing to do is basically to look at the expected cost. And it's easy to calculate. So it's just the probability that you hit the level and times the cost of the corresponding level. Okay. So then we can sort of try to do a little bit of comparison, because there's a lot of things in common with the single-term estimator and the multilevel Monte Carlo, at least in the canonical case. And actually, for the whole talk, I'm sort of focusing on the canonical case where you do have the where the multilevel can achieve the canonical, right? So the Milstein example, which I talked about, is in this case. So basically, we have the squared expectations behaving like 2 to the minus 2L, and cost is 2 to the L. Actually, what we can do now is that we can implement the single-term estimator like so. We can set the probabilities to follow the geometric distribution. Basically, it means that the PLs will be proportional to 2 to the minus 1.5L. And there's a reason for picking the 1.5 here. Because basically, if we look at the variance expression, we plug in the quantity V that had to be finite in order the single-term estimator to be finite variance and well-defined and everything, or have the right expectation. So if we plug in the orders that we have in this case, so basically we will have this sum here, and we see that now that because the PL is not vanishing too quickly, this term will actually sort of override that term. So the sum is finite. So the PL is not decaying that fast. But then if we look at the expected cost and do the same kind of calculation, plug in things here, so you see that actually here, this decay has to be fast enough so that it will kill the cost in order for this to be finite. Okay, so that's nice. If you have a finite variance and if you have a finite expected cost, actually what you can do is that you just simulate n independent realizations and you average, and that will give you a canonical mean square error or variance rate in this case of the canonical order. So that's great. And now, in order to make the sort of comparison easier, actually we can look at the multi-level estimator and not start from the optimization problem and necessarily find the optimal NLs directly, but let's sort of actually make the NLs in the multi-level proportional to the probabilities in the single-term estimator that we used, like so. And then M is just going to be it's the truncation where the NLs go to 0. If we look at this estimator, we see that actually in a way, it's order 1 over n times a term that we saw here in the single term estimator, right? And the cost is also pretty much like n times the cost of the single term estimator. So and then we can also see basically that if we increase n, okay, the bias term will be negligible, and you will achieve the canonical mean square error rate with this setup as well. So this sort of suggests that, in a way, at least when you think about orders in this case, the single term estimators, or n of them, will be pretty much like the multi-level estimator, right? So then you can ask, okay, is there a reason why I should be looking at an unbiased estimator instead of a usual multi-level Monte Carlo? First thing is more like, I suppose, a matter of taste as well. That some people may think that, well, averages of unbiased estimators is more convenient in a way because it's more classical. Because if you just have unbiased estimators, you actually reduce to simple Monte Carlo, and then you can use sort of theory for simple Monte Carlo, like doing stopping criteria or confidence bounds. There is also, in some cases, it may be that unbiased estimators are sort of nice because you can easily simulate them in a parallel cluster and then aggregate in the end. Okay, and maybe the analysis may be, in some cases, simpler. But I would say that this is not such a big or such a good reason for switching to unbiased estimators, because it's more like, I think you can do more or less everything mentioned here with the multi-level as well. But then if you are in the Bayes setting, so if you sort of would like to use a multi-level method inside another Monte Carlo scheme, which happens if you want to do Bayes inference, then it can be quite nice to have unbiased estimators. So this is basically a simple setup that we have posterior distribution for some parameter theta, which is basically proportional to a prior density times a likelihood. But suppose that the likelihood is actually given by some PDE or SDE or something like that, which we can't calculate, but we can calculate sort of a discretization of the L, or an approximation of that one, or the likelihood. Well, the simple thing is, of course, to do sort of classical fix L and do MCMC using that approximation instead of the full likelihood. And then, of course, this is all fine. You get simulated samples in that case from the biased posterior, like so. So in a way, if this L is quite close to this L, you could argue that this is sort of okay-ish. Then what you can think of that maybe there is a, I don't know, maybe there is a bias here that will become sort of visible in some cases. So what you can do now, well, what you can do sort of if you want to refine your estimator, you could sort of imagine that if we could actually calculate the ratio of the true likelihood over this kind of this approximation, we could actually do important sampling correction. And maybe you could sort of attempt to do this by calculating a really fine discretization here, okay? But with multi-level techniques or unbiased multi-level techniques, you can actually be able to estimate the importance weight unbiasedly. So this is sort of a simple example which I haven't even tried, but at least in principle, you could try to do something like this. You simulate a level which is higher than your L that you did the MCMC with. And then you form a WK random variable like so. But at least formally, if we don't care about whether we can interchange the conditional expectation and the sum again, formally we get the right expected value for that weight. And in fact, you can formalize this so you don't need much more rather than a little bit of integrability to make sure that this is enough to make your estimators to converge. So this is sort of nice because you can indeed do something like multi-level with this debiasing here and get, be able to get rid of the bias entirely, at least asymptotically. And the scheme is more general, so you can have latent variables. So instead of the likelihood here, you might have actually estimators of a likelihood, where the likelihood is actually a integral, which is approximated by Monte Carlo to begin with, even for the levels. And this is what we did with my PhD student at the time, Jordan Franks and AJ and Cody. So basically, the key is that we are using a single term estimator inside this sort of scheme and use a so-called delta particle filter to form the delta variables. Another setting where unbiasedness may be quite convenient is that if you want to, instead of doing Bayesian inference, maybe you don't want to do actually maximum likelihood. So if you would like to maximize the likelihood, say, and if you have a nice likelihood, but anyway, a likelihood that is very difficult to compute exactly or something like that. If you are actually able to approximate the gradient of the likelihood or the function you want to maximize or minimize, you can actually use a stochastic gradient, at least in principle. Again, by doing randomization of the levels and plug in your randomized gradient estimator in place of the gradient. And then you have some step size sequence that is from the theory of stochastic gradient. So the nice thing about unbiasedness here is that if you have really unbiased estimates of the gradient, unbiasedness means that given this previous value of your previous approximation of your maximum, this will be the conditional expectation of that one is the true gradient. Okay, so then you can sort of write down your recursion here like so. So it's basically just a gradient ascent, but then this is perturbed by a noise term. And if you have this unbiasedness, these will be Martingale differences. And then there is nice theory for stochastic approximation that will give you convergence results and CLTs. And it may be possible actually to do this kind of stochastic gradient with biases. So if you don't have unbiased estimator, but something that has a little bit of bias. And similarly, you may do what I had in the previous slide, the Bayes estimation with biased likelihood or something like that. But it may be actually quite hard to say anything about or say anything precise about the error, because it may be hard to quantify the bias. Okay. Well, there are some places where unbiased estimators are quite nice. So then the obvious question is there a price to pay when you go from standard to unbiased? Because at least if we are in the really classical setup, we only care about one estimator. And If we have one estimator, we don't care about unbiasedness. That's important only if we average, right? So in that case, where we have only one estimator, we only care about the total error. And it turns out that actually, yeah, this is not so nice. So in a way, yes, it can be useful already in that case. But it turns out that multi-level will give you a little bit more efficient estimator than by using the single-term estimator that was similar. So you can look at, if you sort of look at the similarly as before, the multi-level that has the same limiting allocation as the single-term. You can look at the asymptotic cost, and it will be similar, or it will be same asymptotically to the average of n independent single-term estimators. But the variance converges to this quantity, which I call sigma infinity square. And the variance of the average of independent single-term estimators will be that variance plus additional term, which is positive, unfortunately. It's a little bit of Jensen's to check that this is really a positive quantity. But there is actually a simple way to get rid of this discrepancy. So we can sort of get rid of this additional term in the variance if we modify, instead of doing simple average of single-term estimators, if we modify it a little bit. And this is basically where my contribution is. So first, if we look at the average of independent single-term estimators a little more closely, we just have J marking for the replication or the independent realizations of the random variables we need to construct the single-term estimators. If we write down the average of the single-term estimators, we can write it like this. And this was pointed out at least by Mike Giles in a review, that if you write down this and then sort of reorganize the indices, which is okay, at least in terms of distributional equivalence, because all of them have the same distribution and all of them are independent. So what you get is that you get something that looks very much like the multi-level, actually. In the multi-level, here we have NL, and here we have NL. But as we have random variables, we actually have a random variable NL here, and this is an expected value of that random variable, turns out. Right, and NL is just the number of R's that happen to hit the level L exactly. And what I did was sort of just the formalization of this notion that if we look at the estimators of the same form, so we have a sum over levels, and then we have 1 over an expected value of the NL and a sum up to NL of deltas. What can we say? Well, if we assume actually that the deltas are independent realizations, so there can be dependence on between the levels, but not between the realizations marked by J. Okay, and then n's are just completely independent of the deltas, but they are some random variables. We do have a joint distribution, right? So NL and NL plus 1 may depend on each other, but they don't depend on the deltas. And you can have NL being positive for any L, and you have to have basically finitely many samples in the estimator, almost surely. And then there's a technical condition, which is sort of doesn't look so nice, so it's a bit complicated, but it simplifies when you plug in certain examples. Some of the terms become 0 and so forth. And then there's a technical condition that you have to have a subsequence so that the V terms sort of become negligible. And then you actually have unbiasedness, and the variance is also given by the V sequence. So this is sort of this is actually reasonably similar result to the original proof by Ree and Glynn. And in fact, the most sort of different thing is the calculation of the variance term, or this partial variance term, VLN. And it's a bit of a computation, but it's still direct computation. Otherwise, it's a reasonably simple proof. Not going to the details though. And then you can ask, what are the sort of examples that fit this setup? So at least the single term estimator fits this scheme. Well, that's quite obvious because that was the original motivation. But also you can put a so-called coupled sum estimator introduced by Ree and Glynn to the same scheme. So in that case, basically the deltas are going to be in the coupled sum estimator. The coupled means that the level variables may depend on each other. But then you actually, instead of picking one level, you pick the level of truncation. And your estimator looks like that. But it's very similar otherwise. And these are unbiased, and you can verify the variance with my theorem, basically with the same conditions as with Ree and Glynn. So you can view the theorem as a generalization of the results of Ree and Glynn. The nice thing about this is that actually there's more room for generalizations or kind of different schemes to think about, because you can choose the distributions of the ends and so forth. You're more free. So, okay, back again to the single term estimator. So what was the sort of motivation, how you can maybe modify this scheme to be better? So if you have an average of independent single term estimators and you focus again on the expected value of the number of terms at the level L and the number of terms at the level L here, which these are the same in multilevel Monte Carlo. But here, if we have the average of single term estimators, in black here, I have the number of basically the NL, the realized number of samples at the level 1, and in blue I have the expectation of N1, and so forth for the levels up to the level 8. And you see that there is quite a bit of discrepancy sometimes here between the expected value and the realization. But the simple thing is that with multi-level, actually, you sort of follow nearly exactly this shape of the expected values, right? Because in that case, actually, the NLs are deterministic, so their expectation is exactly their value. Well, you can do actually similar thing by adding a little bit of randomization to the multi-level, so to speak. You can get an unbiased estimator. And the scheme is rather simple, so it may look a bit complicated, but in fact, what it is, it's just based on sorry, was there somebody trying to say something? Okay, so it's based on a very, very simple uniform stratification of a uniform 0-1 random variable, which is then basically transformed to a geometric random variable, or a random variable following the PL. Thank you. Right, so that's basically it. So somehow it is this is not harder to simulate than the average of independent single term estimators, but at least we sort of have these matching much better to each other. And indeed, actually, then you can ask how much, well, this is a stratification, right? So we know that because we do uniform stratification or proportional allocation in the stratification, we know that the variance cannot be higher, so we reduce variance, but then you can ask how much. And the thing is that actually there's a nice equivalence that if you again look at the multi-level estimator, which is similar to which has the same proportional allocation somehow asymptotically than these unbiased estimators or the single-term estimator, then it holds that the stratified estimator has the same limiting variance as the multi-level. So you got rid of the extra term in the variance. Okay. And so then you can optimize rather easily if you sort of look at this asymptotic result and optimize the expected cost times the asymptotic variance. And you may be able to actually choose the PLs proportional to beta L, which are just square root of the variance divided by the cost. So you can estimate the variance rather easily, and cost you know pretty much in all scenarios. Okay, so this is nice. And you can do, basically the result does cover, there is a result also for the couple sum estimator converging to a multi-level Monte Carlo with dependent variables. Okay. Okay, then I do have some experiments, but I'm going to be quick on these in the interest of time. So for examples, the first three are actually from the paper of Ri and Glynn, and the last one I made up. Okay, I just quickly say that, okay, if we look at the last example, so in these examples that were given in the Ri and Glynn paper, in fact, the simple average of single-term estimators was nearly as efficient than the multi-level Monte Carlo. Okay, but in some cases, the extra term in the variance can actually can be substantial, like in my made-up example. Okay, which you can then get rid of by stratification nicely. And what's the take-home message, basically, which I would like to deliver? So in the case when you have multi-level in the canonical scenario, canonical mean square error rate, you can implement an unbiased scheme that looks very much like the multi-level, behaves very much like that. In particular, it's nearly as efficient as multi-level, but unbiased. You have a nice optimization criterion in that case. You can have dependent variables in the levels, okay? And there is also an extension in the paper that allows for the number of samples to depend on the level differences in a sort of a stopping time fashion. It's a bit more complicated. Then there are some questions basically for the discussion later. So I think you could sort of imagine of adaptive strategies where you simulate single-term estimator or the stratified single-term estimator and then refine the probabilities based on the rule that I showed you earlier. So that's one thing. I haven't tried that, but that could be useful. Then a big question, I suppose, is it possible to do to prove a similar cheap debiasing result? So basically a result that would say that you can do debiasing of a multi-level in a way that doesn't cost too much in variance or cost in the sub-canonical case. So there is something in the Ri and Glynn paper, but it's harder because quantification of the thing is harder because the expected cost will be infinite. And then I was thinking of yesterday when I was listening to talk of Elizabeth that it would be interesting to think about whether there would exist a debiased version of the blue, even just theoretically. Yes, thank you.